All right, this page is going to have a couple new things. It's going to have a concept called the removable discontinuity. And all that is when you're looking at the numerator and denominator, the part that could factor out that you can reduce. So x plus 2 equals 0, x equals negative 2. The removable discontinuity is at x equals negative 2, the part that would cross out. So now this one is kind of hidden in there because you would have to factor the numerator first. So if I take a 2 out, that leaves x plus 3, and then x plus 3 over x plus 1. So then the removable discontinuity would be this x plus 3 that reduces. So at x equals negative 1 is the removable discontinuity. Okay, this last one's going to take a little bit more work because you're going to have to factor all of that. So the numerator would factor to x plus 2 and another x plus 2. This would factor to x plus 2 and an x plus 3. So one of the removable discontinuities would happen at x equals negative 2 is the removable discontinuity. All right, so let's look at the back. So the back is everything all at once. And for whatever reason, it did not read this as a plus sign. Okay, so let's see if this would factor at all. So x plus 6 is not going to reduce anymore. But then if I think of all the things that multiply to give me negative 8, that add up to negative 2. So that's going to be x minus 4, x plus 2. Okay, so there's not a removable discontinuity. So I factored the numerator, I factored the denominator. The degree of the top is 1, the degree of the bottom is 2. So this is, when you think about, and I just do it really quickly as Bobo Button eats DC. So bigger on bottom, yep. So this has a horizontal asymptote at y equals 0. So on this graph, there would be a dotted line on the x-axis. Okay, the vertical, let me come over here. So I factor the numerator, factor. The x-intercept is found by setting the numerator equal to 0. So if I take x plus 6, set it equal to 0, that means that there is a x-intercept at negative 6. So 1, 2, 3, 4, 5, 6. Okay, there's a vertical asymptote if I set both of these equal to 0. So at x equals 4 and x equals negative 2, because you would switch the signs. So at 1, 2, 3, 4, there is a vertical asymptote at negative 2. There's a vertical asymptote. And then the removable discontinuities, there's none. Okay, so let's see what else I've got going on here. So this particular graph is going to look like okay, and I just typed this in, but it fits this pattern really well. So it should not cross the horizontal asymptote, and then it's going to stay in between these borders here, and it's not going to cross the vertical or the horizontal asymptote there. Okay, so let's look at the next one. Okay, so there's no factoring that, so it would just stay 2x minus 3. Now, x squared minus 9 is a perfect square trinomial, a perfect square binomial. So the difference of two perfect squares. Okay, so the degree of the top is 1, the degree of the bottom is 2. So again, this is, the degree is bigger on the bottom. So at y equals 0, I'm going to have another horizontal asymptote. Okay, then let's see what else. My x-intercept, if I set 2x minus 3 equal to 0, I'd add 3 divided by 2, so that's going to be 3 halves. So at 3 halves, which is monkey in the middle here, I've got an intercept. My vertical asymptote is going to be at plus n minus 3. So 1, 2, 3. And 1, 2, 3. So at x equals 3, x equals negative 3, y equals 0. So that was x equals 3 and negative 3. I didn't have any removable discontinuities because this did not factor out. And then this graph is going to look like and I typed this in. Now the only difference is on this middle section, we do have a horizontal asymptote at 0, but it is allowed to cross over a horizontal asymptote. It's never allowed to cross over a vertical asymptote.